Okay, so we have this problem, this application problem. Welcome back. In which we are asked to answer the question: how long will it take for Lake Erie to decrease its pollution concentration to half of what it is now? So this problem, I got it directly from the book that we're using. You can find it on page 27, page 33, and so some of this information comes from that book. Um, so once again, we have Lake Erie. There's the situation is that it is pretty contaminated, pretty polluted. There it's and they're asking us how long will it take. So if we supply a clean flow of water constantly, uh, how long will it take for the whole lake to decrease its pollutions? How many times? And you can this can be days, months, years, etc. I think in this case we're working in the units of like years. Um, so you guys can take a guess. How long will it take to for Lake Erie to decrease in pollution? So this is an example of where we can use differential equations. In this case, the non-homogeneous linear ODEs to solve a problem like this. This is a problem that you could see something more related into like the fluids dynamics class, but it's still something applicable that we can use right now to see where we can use this kind of information. So some of the information once again comes from the book. So they're telling us that the volume of the lake it's about 450 kilometers cubic, and that the water flow in and out it's a constant of 175 kilometers cubic per year. That's the water flow going through the lake that every year it receives. So 175 kilometers cubic per year. We need to define our variables. In this case, capital P is the pollution concentration in pollutants by volume. We're given an initial condition here that the pollution concentration at time 0 it's equals to well yes when at the very beginning the pollution concentration it's about 0.04% of the total volume. So that's the pollution concentration right now, and we have that P of T is the pollution concentration at any given time, and then um, P prime of T it's the rate of change of that pollution concentration. Um, they're also telling us that the inflow water has a pollution concentration about P over 4. So it's not totally contaminated, the lake at the very beginning, but it still has some pollution. And the clean water, it's not necessarily like super clean, that it has no pollution, but it has about a fourth of that pollution. So it's still polluted, but it's less than what it is actually in the lake. So over time, since we're decreasing the amount of pollution, it eventually will decrease because we're supplying less pollution than what it actually has. So let's set up our terms here. So then we know that the rate of change of pollution concentration will depend on the inflow and outflow. So P prime is equal to the inflow of water minus the outflow. We know that the outflow is a mix of like pollution and water, while the clean one has less pollution than that. So this is once again something got from the book. But we see then that uh, we'll have here, if we rearrange our terms, we have P prime is equal to the total water flow rate that comes in and out. So that's 175 kilometers cubic per year, right? So that's how much water. So we need to identify how much pollution of water. So this is the amount of water that comes in, but basically we're trying to find the amount of pollution that comes in. And the pollution, it's a percentage in regards to volume of water. So uh, in order to identify that, we're gonna see that we need to multiply that 175 times the amount of pollution coming in, which is about a fourth of what it actually is right now, minus the amount of pollution at any given time over the whole volume of 450 cubic kilometers. So if we rearrange this will be 175 times P, which at the beginning we know it's 0.04%. So in decimal, this is 0.004 over 4 minus the amount of pollution at any time over the 450. So you can see this is like the initial, the beginning, and this is the pollution at any given time. So we're basically solving for PT, which is the amount of pollution. First, to give us a differential equation that will solve this, and then we'll be solving for time. Kind of like the other application problem that we had. So let's continue solving. We'll continue simplifying. And we're going to get that P prime is equals to 175 times 0.0001 minus P of T over 450. And if we rearrange things in here, once we multiply the 175, we're going to get P prime is equal to 0.0175 minus 175 over 450 P of T. Yeah, so we're almost done. With a little bit of rearranging, we can get our differential equation will sort of look something like this, and in which we have that P prime of T plus 175 over 450 P of T equals to 0.0175. And you can see that this is in fact our modeling equation. And you can see that this, it's a, what kind of equation? Did you look at it? Yes, it's a linear, because only two terms have the P of T, and it's linear because there's no, like the P of T's, they're not like to a higher power, and there's non-homogeneous because only two terms have the PUG. So now that we know this, we know how to solve this one. So we need to identify P, or in this case, the term P of X, right? Or in this case, just that constant here. So that P, I'm just gonna name it P to not confuse any more people with the terms. In this case, this is lowercase p, not capital. And this is just in regards to the formula. So this is 175 over 450. In this case, it's just a constant. And then the R of X, or the R, right? You don't want to mix, once again, more variables. It's just 0.0175. So we know that we need to look for our H first. So H, it's equal to the integral of 175 over 450 dx. Well, let me write the formula just in case you haven't seen it. So this is the integral of P of X dx. So this is the integral, right? The integral of 175 over 450 dx. If you don't understand where the formulas come from, you can watch the video that I made before explaining the linear non-homogeneous. And for this one, if we solve it, and if we simplify 175 over 450, that's just 0.389. And we're not integrating with respect to x, we're integrating in this case with respect to t. Well, the formula says dx, but we're actually integrating with respect to t. That's our independent variable. So it will be 0.389 times t. So that's for h. So then solving for our actual P of t, or pollution at any moment in time, or the pollution concentration, yeah, it will be E to the negative H times E to the times the integral of E to the H times R of, in this case, we're going to name it ROT dt plus C, just because we're following those variables for today. So if we plug it in, this is e to the negative 0.389t times the integral of e to the positive 3.89t times r of t, which in this case is times 0.0175 and plus c. So doing all of this, we're gonna get that this is equal to e to the negative 0.389 t times 0.175 over 0.389 times e to the 0.389t, right? This is what the integral is, times c. And once we need to multiply this times this and times this one, we're gonna get then that our P of T, our equation to model the pollution at any given moment in time, once we simplify, will be 0.045, which comes dividing the 0.0175 over the 0.389, plus CE to the negative 0.389T. And this is our general solution in our modeling equation or modeling solution for this one. So once again, this is our general solution. So in order to determine the time that we need to apply our initial conditions, right? So that we can find our particular solution. So applying initial conditions as we were giving there, right? So initial conditions tells us that the volume at the beginning, it was 0.04% of volume. So if we have 0.04%, or I guess 1.004 tons of 450 kilometers cubic, we end up with about 0.18 kilometers cubic of pollution in water at the beginning. So we know that the pollution at the beginning of the time was that. So applying that condition, we get, let's plug it in. So we have then, let's plug it in. So we have here then, so 0.18, that's equal to 0.045 plus C times E to 0, right? When T is 0. Rearranging this, we know that C is just 1, E to the 0 is 1. So solving for C, we get C to be 0.135. And therefore, my solution, my particular solution, will be P of T. It's equal to 0.045 plus 0.135 e to the negative 0.389 t. And this is what I would call my particular solution. So now that I have a particular solution, all I need to do is to solve for t, solve for the time that it will take for the pollution to decrease by half. So we know that the current pollution right now, so I'm gonna write this. So current pollution right now, it's equal then to 0.18, right, when time is 0. So the pollution at what time? Well, what will be the time in which the pollution is half of that? So 0.18 over 2. What will be that time? Right, so half of the pollution right now. So let's apply this condition. So then we'll have 0.18 over 2, that's 0.09. And this it's equal to 0.045 plus 0.135 e to the negative 0.389 t. And this one we are solving for t. So then we need to rearrange. We know that 0.9 minus 0.045, we subtract both sides. This will be 0.045 equals to 1.35 e to the negative 0.389 t. We divide, so we have, and we take the natural log, so we can bring that t down. So we have that natural log of 0.045 over 1.35 will be equal to negative 0.389 t. And then solving for t, right, will be natural log of 0.045 over 0.135, all of that over negative 0.389. So if we do that, we get that t, it's approximately, well, it's about 2.82 years. So then we can finally say and conclude that the time it will take for the pollution to drop by half on Lake Erie of what it is right now, it will take approximately 3 years. And this is how we use this kind of problems to solve practical applications. So once again, you can do this at home. You can, you just need basically to find those conditions on the lake, the amount of water it receives, which is pretty easily findable if you're an engineer, like working in that kind of industry. Or some of these values are usually available in the internet for the public. And you can devise a way in which you can decrease the pollution and estimate based using a differential equation how long it will take for you to clean this lake. So you can see this follows a exponential decrease. You can try to find a way to calculate how long it will take to get rid of the whole pollution completely. For sure, the less pollution there is, over time, you will take longer if you will follow a negative exponential. But this is how you solve that problem. So that's it. I will show you the next video in which we're going to be doing non-linear ODEs. So that's it for this one. I'll see you the next time.